Hi everyone, my name is Bryan McKenna, and as you've heard already, I am head of product at Mina Protocol, at the Mina Foundation actually. Mina Foundation exists to serve and empower the Mina community and the Mina Protocol. The subject of the talk today is building the privacy and security layer for Web3 via zero-knowledge smart contracts, but which we like to call ZK apps for short. Now, before we get into zero-knowledge smart contracts, let's have a look at what we're going to talk about today. So I'm going to give everybody an introduction if you're new to Mina, or a refresher if you've heard about Mina before. We're going to zoom out a little and look at the state of privacy today as it relates to Web 2 and Web 3 and why we believe it matters. Then we're going to get into what a ZK app is, how it works, and we're going to do a worked example of a cross-chain ZK app. And then we'll talk a little bit about how to get involved and what are the next releases that are upcoming on Mina. So, to give everybody an overview of Mina, Mina was incubated by a team called O1 Labs, and O1 Labs started working on Mina in 2017. They worked on a lot of zero-knowledge cryptography in that time, and in March 2020, Mina Protocol launched into mainnet. We like to call Mina the world's lightest blockchain, and we'll get into a little bit about how that works in a while. But just to say importantly as well that it's a layer 1 blockchain protocol with zero knowledge built natively into the core of the protocol to give us these lightweight trust and privacy properties which are important for blockchains today. So, I mentioned the lightest blockchain in the world. What do we mean by this? So, let's first think about how other typical cryptocurrency protocols work. So, other layer 1s, well, they have blockchains, and those blockchains grow in size over time. As each new transaction gets created and blocks get minted, the chain moves forward, and the data storage footprint of the chain grows the longer the chain is in existence, right? So to give you an example, Bitcoin today is around 400 gigabytes for a full node storage, and Ethereum is over a terabyte. So this means that anybody who wants to join the network needs to sync all of this data from Genesis, and people who want to interact with the chain with full node security need to store all this data. So, in contrast, we call Mina a fixed-size, succinct blockchain. Fixed size in that it remains constant size over time as the chain moves forward, and succinct in the way that it's very lightweight because its data footprint is so low. So, how do we achieve this? So, instead of every node on the chain storing the full entire state history of the chain, instead, on Mina, every node stores a zero-knowledge proof which represents the blockchain. And that zero-knowledge proof says three things. First, it says there exists the Mina blockchain, which moves forward over time. Second, here is a proof that verifies the entire transaction history of the chain since Genesis. And third, here is a proof that shows the chain current state of the blockchain. So what benefits does this bring? So the first thing is that every node can participate as a full node, only storing 22 kilobits of data. So we don't need to store the full terabyte of data or whatever the blockchain state history might account for now. And this means that it's very easy to participate in the blockchain as a full node. So you can do so with minimal hardware, think your browser or your cell phone, and you can sync the entire history of the chain in milliseconds rather than having to download the entire block history. Another important thing for decentralization is that we don't need to rely on third parties to contact the blockchain for us. So think like something like the way we use Infura to interact with the Ethereum blockchain, for example. And the third cool thing is because we have zero-knowledge proofs built in natively to the protocol itself, we can now start to think about doing things that zero-knowledge helps us with regarding privacy and proving off-chain data computation. And this is really the core of what ZK apps are. So let's move on to some other things. Now, I've mentioned privacy, and privacy as it relates to smart contracts using zero-knowledge proofs. So what do we mean when we talk about privacy in blockchain, and why is it important? So privacy is well documented in the UN Declaration for Human Rights, for example, as a fundamental human right related to your identity and to your actions. Now, in Web3, privacy can be defined as the ability to decide what you want to share and who you want to share it with. So we're all aware that in Web 2, data is stored by centralized servers, and it's really not in the power of the user. It's in the power of the Web 2 companies who use it for, their own business logic, and sometimes they don't even custody it that well, as we've seen in the many data hacks which have happened over the years. And as we now transition into applications being either fully Web3 or somewhat Web3, we can start to think now about the decentralization of this data control and handing power over that back to the user themselves. So the user chooses what to reveal, when to reveal it, and whom they're comfortable revealing it to. So this brings us to Mina smart contracts. Zero-knowledge smart contracts, or ZK apps, as we like to call them for short. So before we get into ZK apps, let's talk about how typically smart contracts work today. So let's look at an example like Ethereum. And to contrast this from Mina, we say that Ethereum uses on-chain computation. So in this example, we have an end user, and they're sending a transaction to the chain to update the state of a smart contract on the chain. Now, this transaction is going to contain a payload with some set of instructions for which to update the application. Now, every node on the Ethereum network will execute these instructions, and if they're valid, they'll get committed to the chain, and we'll have a new state for this application. Now, there's a couple of things here which we might point out to differentiate Mina as we move along. So the first thing is efficiency. Every single node needs to execute every single transaction. Moreover, every single node that newly joins the network has to re-execute every single transaction that's taken place since the start of the blockchain. The second one is privacy. So as an end user, when I send my computation to the network, any data that I use in that computation is fully visible to every node and every participant on the network. So there's no notion here of any privacy or data security. Now, to contrast against that, in Mina, we use off-chain computation. So smart contracts get executed off-chain on the user's machine or device. So looking at the very same example, as a user, I want to send a transaction to the chain to update the state. Instead of sending the transaction and all of the execution happening on-chain, the transaction happens locally on the user's device. And the only thing that goes onto the chain is a zero-knowledge proof of the correctness of that computation and the new state that I want to update to. So the advantages of this can be, we can relate that back to the Ethereum example. The first thing is privacy through zero knowledge. Because the computation happened locally, and any data inputs that I used in that computation stay on my machine, and only the zero knowledge proof gets sent to the network, then the network doesn't know about any private information or special instructions that I included in the transaction. It only knows that if it's a correct transaction, it will apply it to the chain, and we'll see a valid transaction. The other thing is efficiency. So we spoke earlier about everything happening on-chain and all those instructions having to be executed by every node. Well, in Mina, we said that only the zero-knowledge proof gets sent to the chain. Therefore, the size of the computation, which happens off-chain, is pretty much limitless. So no matter if it's a very simple computation or a very, very complex computation, In the end, the only thing which gets sent and has to be validated by every node is the zero-knowledge proof itself. And that can open up a variety of new use cases, because now we don't have to worry about the size and complexity of the computation that goes on-chain. And also, we can think about applications which might take advantage of the privacy aspects of special data not leaving the client side of the user's device. Moreover, we can think, we all know that the gas cost of computation depends on the complexity and the size of that computation. In Mina, gas cost is proportional to the number of proofs which the nodes have to execute. So again, we have predictability and efficiency around gas costs. So a ZK app consists of two parts: the smart contract and the UI. The smart contract can be written using our library, Snarky.js, and the surface language for that library is TypeScript. Conveniently, the UI can also be written in TypeScript. And somebody can write the whole smart contract in one repository, put it in NPM, and import that into the UI. We chose TypeScript because, firstly, it's a very well-known language. It's used by many, many developers throughout the world. And we wanted to have a very low barrier to entry for writing Mina smart contracts. Another cool thing is that the really complicated cryptography circuits around zero knowledge are abstracted away from the software developer, so the developer doesn't really need to understand the zero knowledge crypto, which can be quite heavy. So we think we have a really low barrier to entry programming language here. So how does a ZK app work? So a smart contract boils down to two artifacts: the prover function and the verification key. The prover function runs locally and generates a zero-knowledge proof of execution, and that's what gets sent to Mina, to the blockchain. The prover function basically does what you tell it to do, and if it does that thing correctly, then it will get accepted by the verification key. Now, the verification key is what's stored on-chain, and its job is to verify the correctness of the execution. And the verification key really is where the business logic and any constraints on the smart contract are programmed. So when we deploy a verification key to the blockchain itself, we get what's called a ZK app account. And that ZK app account, the state of that account can only be updated if a valid zero-knowledge proof gets submitted and that proof matches the constraints and the logic which exists in the verification key. If an update comes to the ZK app account which doesn't match those conditions, for example, there might be some malicious computation or somebody is trying to update something which is not correct, then the chain will see an invalid transaction and reject it. Just a little bit more about Snarky.js. Everything is can be run in the browser in Node.js. You can use all your cool existing libraries and tools for TypeScript that you're familiar with, and everything is open, and we wanted to reuse things which are out there already, which is really nice because we get to leverage existing libraries and existing tooling for our smart contracts. So let's touch briefly on a few example use cases. I think it's fair to say that we don't know what developers will build when they bring all their creativity and innovation into the new types of things that ZK apps open up, but just run through a few quick examples. So DAO voting is all public now. What we might want to do is execute the vote off-chain on Mina without revealing the identity and also which direction the DAO member voted. And we'll do the chain calculation on-chain, so protecting the member's identity and which way they voted. We might want to prove to DeFi about somebody's credit history, or if they have enough collateral to get a loan, for example, and solve the over-collateralization issue, which exists on DeFi right now, while protecting the user's identity and also their account balances and things like that we want to prove over. For enterprise, Enterprises don't trust each other, but they might want to collaborate on a public blockchain over data sets where they want to prove certain things about those data sets that they're both interested in, for example, without revealing anything about the data sets which they want to keep private. So that's a really nice one. A really cool thing about Mina is because of the recursive nature of Mina's proof system, it's very easy to spin up ZK rollups on top of Mina. And this is particularly interesting for gaming and application-specific use cases which would require their own rollup, and they can settle back to the main chain. We can also prove things about on-chain information, and also cross-chain as well. So we can prove that I own some account, or I own some NFT, or my balance is above X or Y, for example. And another thing we might do is we might have a private payment system on top of Mina, a la Zcash. So we've spoken about ZK apps. We think the ZK apps will be really useful to other L1s who might want to leverage the ZK apps and the privacy and trust capabilities that we have on Mina. And we want to bridge to other L1s in a fully trustless way and leverage the succinct properties that Mina already has. So firstly, why would we want to do this? As mentioned, Ethereum apps will want to use ZKPs because they're cheaper on Mina, and they have a super high gas cost on Ethereum and other EVM chains. And because Mina's state can be proven inside 1.0 knowledge proof, we can easily have a trustless bridge to Ethereum using this property. So, and interesting to say as well that this has been built at the moment, and it's been funded by Ethereum Foundation and Mina Foundation, and it's been built by a team called Nil Foundation. And I believe there's a demo on their website already running inside an Ethereum testnet. So we'll have a EVM smart contract, and the purpose of that smart contract will be to allow anybody, to update the Mina state into that smart contract. Now, the logic of that smart contract will run Mina's chain selection rule to say that this is a valid Mina state, and it will also have the Merkle root of the Mina ledger, which gives the latest state of Mina. So we're going to verify the correctness of the state, and we're going to verify that this is the latest, strongest Mina state. So now we will have an in-EVM smart contract which stores the state of Mina. So multiple applications in the EVM can now query this contract to pull state out of Mina without ever leaving the EVM. So let's go through an example of a ZK app and a cross-chain ZK app at the same time. So let's imagine we want to create a DAO where membership of that DAO is predicated on proof of attendance at the Upbit Developer Conference. So how can we do this? And point out that this is going to be an Ethereum-based DAO in the EVM. So we'll create a new ZK app account on Mina with the verification key was at UDC. And in the data field, I'll put my Ethereum public key. So I'll send some proof of identity and some pass that proves that I was here to the ZK app on Mina. And the Mina bridge gets updated with the latest Mina state on Ethereum. So now my ZK proof of attendance and my proof of identity is on Ethereum. That data is now uploaded in the Mina bridge account on Ethereum. And the UDC DAO on Ethereum gets a transaction from me on Ethereum now with my Ethereum public key, and then it checks the Mina smart contract to say, do we have a Merkle path from Mina? Does the Mina account have the right verification key? And I, as a user, signed the transaction with the same public key as what was in the Mina ZK app. If all this is yes, then UDC DAO will register me as proving that I was at UDC in a private way directly from Mina. And that really wraps up my presentation. A little bit about what next for Mina. So right now we have ZK apps on testnet, and this is a beta testnet, and we'll be moving to a fully incentivized testnet within a couple of months. And then very soon after that, ZK apps will be available on mainnet. ZK Bridge, as I mentioned, is in like a demoable state at the moment, and that's going to launch at the same time as ZK apps. Another cool thing about ZK apps is that it will enable custom token creation on Mina. So projects can create their own tokens and launch them and use those tokens for their ZK app projects. How to get involved? As a developer, the best place to go is to join ZK apps developers on Discord and Twitter. The documentation is really good, especially around Snarky.js with worked examples and things like that. And those two are the main repos that developers should be interested in. So thank you very much for your attention.
We do have a question for you, though. What competitive advantage does Mina have over other zero-knowledge protocols?
Thank you. Yeah, this is a really good question. So the first thing that comes to mind here is the ease of use of the programming language. We've put a lot of thought and a lot of care into ensuring that there's a really low barrier to entry for Snarky.js. That's why we chose TypeScript as the surface language for this, because we want to be open to as many developers as possible. And we want ease of development, ease of deployment in one repository and everything like this to be as open access as possible. And a lot of the tricky bit before launching Mina was during the programming language design, creating the abstractions from the really complicated zero-knowledge circuitry under to be able to be used by a normal protocol or smart contract developer who doesn't really need to understand the intricacies of the cryptography underneath, which is really cool because prior to the last couple of years, the kind of skill set that was required to program using zero knowledge was like a very small subset of the world. So we want to open up to as many people as possible. So I see that as the main competitive advantage.
Well, thank you for that answer. I hope that answered our audience's question as well. Please give another big round of applause for Bryan McKenna. 네, 다시 한번 큰 박수 부탁드리겠습니다. 네, 감사합니다. Thank you.